Hi Gautam, Mehul this side. I'll quickly give you a demo run of the pipeline for cat eye color classification. Before I start running the program, I'd like to quickly discuss a little bit about the data set at hand and what were the requirements of the assignment and what went into building the pipeline. So we were given around 9 to 10,000 cat images. For every image, we had 9 coordinates corresponding to the shown picture here. Now this data set was most probably human annotated because the coordinates were not always at the center of the eye, and sometimes were in the iris region or in the pupil region, but not always at the center. And a lot of times, the images were not very conducive for perfect tagging either, because, like for example, in this image, we do not know the apex of the ear where it's merging with the background. So they were good enough, but they were not always perfect. And the reason for saying this is that a lot of times, not all, that there are times when the neural network itself does not give you the exact centers of the eye or the apex of the ears, and it's a little bit misaligned. And the reason for saying that is because then we have to, when considering the bounding boxes, then we need to take up a bigger delta or the bigger error area to include the bounding box. And when the bounding box becomes bigger, you include a lot more fur in the image than you would want, because as the requirement for the assignment was that we need to do a color classification for the eye, then it's better that your final bounding box out of the pipeline that is extracting out the eye has the least amount of fur to not give it an effect. So, and then there were some inconsistencies also in the data set. There were a lot of cats wherein the eyes were very small or almost absent. So now this was happening for multiple reasons. So, because the perspective from the camera, if the cat was far away from the lens, then you had a very small eye, and then when you cropped out the eye, it became very hazy to even label on the human level. And in a lot of cases, the eyes were just shut, as shown in this image. And I'll show you the next case. Like you can barely tell what the color of this eye is, and because this is happening because the cat is very far away from the camera, and when you crop the cat eye, it becomes very small. Okay. So yeah, and then there were a very few percentage of cats in which the alignment of the cat is not vertically with the camera, and it's rather horizontal or it's flipped, and the neural network is able to catch the cat eyes with sufficient accuracy but not perfectly. So in the sense it is not able to understand that one eye is smaller than the other, and so even if the point for the regression model will be in the area of the eye, it will not be perfectly centered. So when I first saw the project, the first thought that came into was that, can we solve this problem without using neural nets? Can we have an implementation which is very fast in terms of predicting and is very fast to train also? So I looked into the cat eyes, and this is where the problem lies. We cannot just do a shape recognition in the image using edge detection and things like hue transforms, which can detect circles and ellipses and other parametric forms of geometric shapes. So all the cat eyes are not circular or elliptical as in the case of human eyes, and even with their pupils, they're not always slits. They are sometimes round, they are sometimes elliptical, they are sometimes conical. So that is the problem with the cat eyes. So that's the first part in the project, that you need to somehow get out the eye from the cat. So um, this thing went out of the window after doing some research on the cat eyes and trying to see if some circles can be made um, with the known distance between the eyes. And after this, it was that okay, fine, we cannot do this via some other edge detection technique. So now we came down to the fact that how is the pipeline being built right now. So for the face extraction and for the eye extraction, I used a simple regression neural network. It is a CNN based network, but I've used transfer learning because it is sort of like an object detection problem only, wherein we just in object detection you need to have a you need to first make a bounding box around the object that you are interested in, or sometimes not even that, you just need to tell what the object is there in the image and not where. So but in this case, so there are networks already trained to do this job very well. So when you say that networks are already trained, their weights are trained to give you the correct features for the image that divide this image into different classes or different regression, and then you can use those features to give you whatever desired output you want. So what I'm saying in a sense is that something like that you have. So how CNNs work exactly is that you CNNs are more of a feature extractors in an abstract form, if I can say. CNNs are more of a feature extractor, and then after the feature extractor you have dense layers, and you can train the dense layers according to the needs if the feature extraction of the image has been done in accordance with this dense layer earlier. So what I'm saying is, like, if this huge network like VGGnet or ImageNet has been trained in lines with what you are looking for, then the feature extractor will be extracting things that you are interested in. So we do not have to train the whole network again, and we can just use the last layers, the dense layers, which are the decision-making layers. Um, we can just retrain them to the needs that that line up with the requirement. So what I did for so in this pipeline, I used two levels to do this. So I used two levels because empirically it was coming out to be more accurate, and also having said that, I did not train the whole network myself. It was better that I gave it a face image, and then from those that face image, it extracted out the cat eye information. So this is a regression model because we wanted the coordinates of the image that comes out. So what is happening exactly in this is that the whole image goes in after some pre-processing, obviously, and the first net for the first network gives you the coordinate of the top left and the top right in the image. So in this image, it is giving you the coordinate here. It says that I am confident that the coordinate here and here are the, and so that the bounding box, this bounding box is what we are interested in. So we get the first bounding box of the cat, and then the second neural network, which is also a regression neural network but trained on the landmarks, um, gives you 9 regression points. So actually 18 points x comma y. So it gives you 9 regression points on this image, and the loss function is according to the the file that we're given, the annotations. So after this 9 regression points, we come down here. We know that the 2 points are corresponding to the eye, and now we do not know what is the bounding box for the eye. So we make an approximate bounding box, but we also need to be taking care of the fact that if the cat goes away from the camera, then the bounding box needs to become smaller. So empirically, we found out that there is a ratio between the distance of the eye and the radius of the eye. So it was approximately 4 to 4.5, and that was nicely covering out the radius of the eye. Actually, it was 5 for the radius of the eye, but you wanted to have some margin for taking out the taking the whole eye. So we took it to be 4.5. I took it to be 4.5. And also during this process, I understood that we can have things better by the fact that there must be some ratios in which this other points correlate with this point. So if in the cases wherein this is misaligned, then we can know the misalignment and correct it by the other points that we grab from the neural network. So that's one of the reasons why I use the regression network for all the 9 points and not only 2 points. And to be frank, I was not worried about till this point because we had very clearly labeled data for the same, and it was a sort of a project or part of the project that has been already coil wet documented in the research community how to perform this. So this was a quick implementation till this point, but from this point onwards, it was a very hard journey. I mean, it was very hard to correctly get the classifications for the color because the cat eye colors vary a lot and they vary between ranges. In a sense, it's not that they have multiple colors and they have a lot of colors in their eyes, but that they have colors varying between two colors. So like if it so most of the cat eyes even in the data set are yellow or copper or anything between. Same thing happens with blue and green and anything between them. Same thing happens and then there were problems with the cat eye itself, in a sense, like there were eyes, like in this case this eye is not yet fully developed and then the iris is almost absent in this eye. So you are only seeing the pupil and that is not the color of the eye. The color of the eye is given by the iris of the eye, and this is only the pupil right now. So there are other issues like the illumination of the photo and the white balance in the photo, which I which were problematic for teaching the neural network on how to do color classification. So the final part in the pipeline is a deep neural network. Actually, it's a 18-layer neural network, CNN for color classification, and I picked it up from a paper actually, and this paper was for color classification of urban vehicles on roads, and it was showing good results. So I implemented the paper after, and this was after a lot of trying and testing of other ways to do color classification than directly using a neural network, because you need to have labeled data for this neural network. For any neural network, for that chance, you need to have a labeled data, but we did not have labeled data for what the cat eye color belongs to. So to venture a little bit quickly into this, I went ahead and I'll just show you one plot. So, so this was almost in the mid of the development phase. To when I was trying to um, tweak and play with a few techniques to see how I can go about unlabeled data. So this is a TSNE plot. So a TSNE is like like an abstract form a dimension reduction technique. So what I have done is I have reduced the dimensions of the feature of the images, and right now these features are not being taken from a CNN network. So like in this example, the convolutional network, or the convolutional neural network for color classification, the convolutional network itself is giving you the features that it thinks are important for the color classification. But in this case, in this TSNE plot, CNN is not giving the features. I am drawing the features from actually a histogram of the image, and after testing a few different techniques, I came down to the realization that HSV in polar coordinates is the best way to extract features, at least for color classification. So, like this is a quick example of what HSV is: hue, saturation, value. We can get into this later maybe. Um, So, and also there's a whole script on the color analysis of each eye. If you would like to go through that by any chance, I will. Yeah, this is the whole script for the color analysis that was performed on on a single eye to understand which color space is important and how you can divide up the color. So actually, this is for this color eye, and then we can see that the colors are majorly four colors, like the brownish of the fur and the black around the eye and in the pupil, and then yellow and greenish. And I think that the network will be giving it green because we have trained the network to pick up any amount of green and then just say it green rather than yellow, because greens are lesser than yellows. So yeah, and so yeah, we can go through this notebook also. I have put this notebook on the GitHub. So yeah, and this is the polar HSV that I was talking about. So you can see that there's a good separation of colors in polar HSV by brown, yellow, green, and the black on the outside. This is with the value of the image multiplied. So yeah, back to the TSNE plot. So the TSNE plot, we saw that there are some clusters being formed, like clearly this one cluster is being formed, which is of grayscale images in the whole data set. So these were also had to be removed because yeah, you cannot perform color classification on it. But the problem, and you see the problem very evidently in this, that the images are being clustered not on the basis of the color of the eye, but rather on the color of the whole image in a sense. So, like you see that there are red patches, the red colored images are here, the dark colored images are clubbed here. So you are seeing that rather than classification on the basis of the eye color itself, the clustering is happening on the basis of the colors of the image. So yeah, that there was a big red flag that this will be a problematic um, thing to do an unsupervised form of learning. And plus, you can see that the images of the cat eyes are not very conducive to color classification. But so we had to come up. I had to come up with something else. So yeah, so I finally came across this paper and then used this CNN for color classification. And if you'd like, I can show you the architecture for the color classification also. But this is getting too much detail. But yeah, this you can see this from the training script. The, the architecture for the training script for color model is exactly the same paper. And yeah, these are the CNN layers. Okay, okay. Let's get into running the script. Okay, I'm running the script from Google Colab, and if you want, you can also run the script exactly like I am doing it. Only the fact is that you will need to download the models, uh, and I can actually share the links with you, and then the script is very self-explanatory, and you can, if you want, you can run these models on your own system also. So yeah, this is running on cloud. If you want, I can quickly go through the script also. Here I'm just downloading the models, and these are the pre-trained models. I'm loading them, so you can see them here that I'm loading these models. The bounding box model, the color model, cyan and ice, and nothing, no need to go into the depths of that, and the landmark models. So so this was one of the reasons why I was not wanting to go CNN myself, because as you can see that this color classification model itself is 350, 330 MBs, and these models become very heavy when you train them because and try to get more accuracy, and that is the reason also why I use the pre-trained model for the regression work, and that this comfortably sits in that 2030. So yeah, there are some utility functions for resizing the image for calculating the eye radius. So as I discussed, the eye radius was 4.5, and here is the distance between the left eye and the right eye, and then I'm taking the radius to be 4 point divided by 4.5. So the distance and the radius ratio is 4.5. And yeah, so resizing, so for training the network for the regression network, I was adding borders while resizing the images, and this is done here. So there is one function which adds the borders and the other function which does not, and is actually used for enlarging the eye. So, and uses a cubic interpolation for enlarging the eye, because you need to maintain the colors in the eye, and cubic interpolation does that the best in what is being offered by CV2. And also there's a small if else logic for eye color classification. So the eye, the train, the network is trained on only one eye, left or right. So what I'm doing right now is I'm feeding it both left and right eye, and then using some logic, simple logic actually, I am printing out the dominant color in the eye according to also the availability of the color in the eye. So what I mean by that is that if green comes in the eye and a yellow also comes in the eye, then prefer green. Example. So yeah, and okay. So already discussed this, and so so for this purposes, I will just check this with the random images from Google for cats, and yeah, okay. So why not go with something yellow, maybe, or I took this image for the diagram. Yeah. Hmm. Okay, let's take this one. So this is completely black, and then this is with a this is a huge image actually. So that's a problem. It's a 4K image. It will take a lot of time to load, and but okay, let's try this. So I'm just curling the image to my workspace, and yeah, it's a wait a second. Average down. Okay, let's see. Hmm. Okay. So yeah, as you can see, the cat eye is detected, and then it says that it's yellow, yellow, and yeah, yellow here also. So I'm just printing this out to show you what the network is predicting without I try to fiddle with it with the if else statements. So yeah, let's do this with another cat eye. How about another color? Maybe blue. These cats look rather scary for some reason. Okay, um, so yeah, this is being saved in the example.png file, and yeah, so and I read the example.png here. So yeah, blue, it's reading it out. Also, about the bounding box, in this image, I had shown that the bounding box is this, but actually we do not have this. We, given the fact that we only have points till here, there is a lazy bounding box or a lazy bounding box for the cat eye, for the cat image. So the bounding box is generally from the apex of the cat to the ear, to the nose. Doesn't really matter. It's an inside detail, like so that's how when there's a small ratio multiplied with it. So, but you can see very nicely that even though the cat apex is not here. The network has understood the features of cat and is able to give these bounding boxes. Interesting. So yeah, okay, let's try it with something else. How about a little bit of greenish, cyanish? Okay. So yeah, as I said, like if by chance the model picks up any other color and then it automatically says green. So yeah, the dominant color that the network finds is green here, and let's do another image, maybe of done, yellow done. How about how about or say a cat with black beady eyes? Yeah, the first one. Let's just try running it on the first one. So yeah, this cat eye is almost black. So I have yeah. So this is yeah dark slash black. So I've actually have the same class for images that are very lowly lit and the images where the cat eyes are black. So oh yeah. So the classes that we have for the cat eyes cat eye colors are this. So we have blue, we have cyan, we have dark slash black, we have green, and we have yellow. So we saw green and yellow being coming out. We saw blue also coming out, and yeah, and cyan is in the middle. So it'll be a little tough to spot where cyan is. But yeah, there were quite a few examples for cyan. Yeah, maybe this will turn out to be cyan. I don't know if it will come out to be cyan or blue. Let's just let's see. I don't know. Cyan was a little bit tricky. Yeah, it's coming out to be blue. Yeah, but yeah. Also, I have added the script for the color analysis for this, and I will quickly show you how to go about this. Like, so I am actually just saving the image that we have last downloaded as an IPNG, and this is not really a good image, but we can actually work with this. Let's for fun add more clear to us. How about this one? I think this will come out to be cyan. I think between blue and green actually is being labeled as cyan. Yeah, okay, it's coming out to be cyan. A little bit low probability, but yeah, the I think the final answer will be Sam. Yeah, it's taking a bit of time because the final image is very. So I think this is a good example to work on. The image is huge, and then so there will be a lot of pixels of every color. So yeah, um, quick color analysis of the image that we have at hand. So we can see that these are the RGB plots, 2D plots. Let's just get into the 3D quickly. 2D is no point. That. It's not that straightforward. But yeah, so you can see that there are hints of blue here. There are hints of yellowish, very light yellow, white, and somehow blue. I don't know for what reason, but blue here also. And then yeah, so you can see that similar thing is happening here. Black for the pupil, and tones of blue to green, and for fur a little bit of brown, red. So, and if we do clustering on these colors, assuming that there are four clusters, green, yellow, black, brown, let's see how four clusters come out. So these are weighted averages and weighted averages on the image. So you are seeing that the four clusters are being distributed as something for the three. I think this is running for three. Yes. Okay, so this is one for the black, one for the middle, and then one for the very light range. And yeah, okay. I think this video is going very long, but so this analysis goes on in depth, and but the interactive plots are not here, and they were important because you cannot see the centers always very clearly. So these help a lot in that scenario, like so you can just see the centers where they exactly are, and then if the color is separable or not. These are running JavaScript. I don't know, Colab doesn't support JavaScript, and yeah, the k means the weighted centers. By weights we mean that we have taken the color value of every pixel and then weighted it according to the number of pixels, and then the color of the center is coming out, whereas k means is just a cluster that is being found. Weights. Okay, I think we have tried different uh, examples where of the cat eyes. Uh, yeah, okay. And if any other explanation is needed, let me know. And this testing script is very straightforward. There is nothing much happening here, and this is little less commented. I have commented out the script that is on GitHub extensively, and I was and these diagrams and plots. If you want, I can put them on the. I will actually put them on the GitHub repo. Okay, thank you. That's it. And let me know if there are any other questions or details that are required from the project. And yeah, okay. See ya.